Hey everyone, good morning. So welcome to the talk, and it would be a bit interesting, right? So
Hello, everyone. How are you? Fine, thank you.
Oh my god!
yes, so hello everyone. So in this talk, we'll be seeing some cool attack vectors that are not so popular in this world of smart contract security. Like we all know, there's reentrancy, there are DeFi bugs, but Solidity needs some love as well. Come on, that's our favorite language. Cool. So a brief introduction. Who am I? My name is Tejaswa Rastogi. Pretty hard to pronounce name, so just call me Tej. What I do, I'm a security auditor and researcher at Consensus Diligence. Besides that, I work on some open source stuff like RETURNDATACOPY, CipherShots, and Unchained. What are these? These are just some platforms for the community so that we can grow and learn from each other. CipherShots is a CTF platform. Unchained, again, a blockchain security conference that we host. So a couple of things, yeah, it doesn't matter. Like, if you want to follow me, you can find me at Twitter, raise a tweet, where I tweet some stuff. Okay. Cool, so this is the agenda. There are a couple of things that we'll be discussing, and I will try my best to keep it a bit spicy. And here you go. So the first one we should discuss is something related to CALLDATA, right? So what is CALLDATA? A brief introduction. Well, if there is a function and you want to interact with it, you have to you're supposed to pass some input data, and that input data is called as CALLDATA. Simple as that. So below you will find ABI encoded CALLDATA with the first 4 bytes as a function signature. Rest are the parameters, which are ABI encoded. Yeah, that's how it works. Cool. So these are the parameters, and this is how it looks when these get ABI encoded. And right, so let's talk about some dirty higher order bits and how these actually matter. Right, so suppose you have a function which accepts a uint8 parameter, right? So what compiler needs, or what's the utmost concern, is the last 1 byte, right? Nothing else. Like if you're passing any other data with the CALLDATA, it should not be, it should not matter, right? But it actually doesn't work like that. So here you can see this one, the first one, is the actual ABI encoder parameter, or typically or logically that's how it should be. But if you're adding some more bits, that's going to work as well, right? Like where it can work, for instance, you're writing some very optimized code, you want to work in assembly, right? You're directly storing value using stores in the slots, right? So this one actually works like this in compilers greater than 0.8. So how it works? Firstly, Solidity takes a parameter from the CALLDATA here below. It extracts the 1 byte, the last 1 byte. That's what we need because we are dealing with just uint8. And after the extraction, it does a EQ to validate it again that whatever we have extracted is actually the CALLDATA we want, right? So we have passed hex 17 as a uint8 parameter. We did an AND with FF, the last 1 byte, to extract the parameter that is 17. And after that, the compiler actually did or performed an EQ, or equal operation, to verify that the actual CALLDATA is the same with whatever we have extracted. But it doesn't work like that in compilers below 0.8. So in below 0.8, it just extracts the value, whatever you have passed, and it forwards to the next operations. So imagine you're passing, let's say, a price, and you expect that the UNT8 will be limited to 0 to 255, but the attacker can pass extra higher order bits, and if you're using assembly and storing directly, you will be getting a higher price, because that's how the higher order bits work. So there's no restriction in compilers less than 0.8, which has been recently added in the 0.8, and that's how it works. So this is the first one. Let's jump on to CALLDATA malleability, right? So again, many of the times we keep the message.data or CALLDATA as a kind of a unique identifier to say, okay, this identifier had recently got validated and now it should not be passed again. So this is a simple scenario, right, from a CTF. So let's say there is a pawn function asking for a valid bytes 32 token. It could be any token. So firstly, what we are doing, we are verifying that it should not be empty. It should contain some value. And it should be the one that I have, like in my protocol, the verification token for the message sender, so that it should not be passed any other random value. Then what we are doing, we are hashing it down and keeping it as a unique identifier. Right? So that's cool. That's how the developer thinks that it will work always, because if you try to pass a different token, that will be a different CALLDATA, and the identifier will be different, so it won't work according to the mindset of a developer. But what if I pass the same token and add some data or append some data at the end, right? So this one, you can see, is exactly the same CALLDATA with the same function signature, same parameter, but these are two different hashes, because I have appended some random data which will not be utilized in this function, because it will just be taking the first ABI encoded 32 bytes parameter, which is a valid token. So the second check, token is equal to verification token, will work because the token is right, but it will make a different hash, right? So this check, the next one, that this should not already be utilized, will be bypassed, and yeah, just because there are two different hashes. So CALLDATA is a unique thing, right? So if we are writing something in assembly, we should take care about these kind of stuff, or we should add some checks so that we are dealing with the parameters we want, right? Great. So this is a CTF challenge, right? If you want to try out, I've created one. You can play it. And it's available as Cybershots. Like if you want to check, go into the slides and you will find it. Cool. So next thing is we can talk about some gas griefing. So before that, like what's gas? Simple introduction. Gas is like a fuel. Every transaction needs it to run some opcode, some instruction set. So every transaction needs some gas. Simple as that. All right. Now in order to understand gas griefing, we have to consider EIP 150 as well. So what EIP 150 defines is every subcall. Like what's a subcall? Subcall is when a contract is trying to interact with another contract, making a subcall or making a message call, like this one in green, target.call. So it's making a subcall to another contract. So what EIP 150 defines that every subcontext, every subcall context can only consume this much amount of gas and nothing more than that. So, but what if we do something good with it, right? We'll see. So here below is just a simple demonstration of how it looks. Great. Now let's talk about gas griefing. So what if we do something so just that we do not allow the transaction to execute entirely but partially, right? So let's say there is a function which is kind of giving you some shares by taking some tokens from you, like you're buying some shares, right? Like you're giving it 100 tokens and you're buying some shares, right? So the above operation, the sum operations, the listed down, what these are doing, these are giving you some shares, and the last call is trying to take tokens from you, like as a trade-off, like a trade is going on. So it allocated you some 100 shares, and now it has to take 100 tokens from you, right? But this target.call gonna not gonna happen, like not gonna execute entirely, and it's gonna fail. Why? Because we know that the subcall can only consume like 63 out of 64 amount of gas, typical like that. So we are calculating the gas, and we are giving it a gas accordingly so that the top level transaction will work, but the subcall will not be getting enough gas to execute, right? So this will fail silently because we are not checking the status of the call, right? So that the call where we are actually taking tokens from the sender or from our user is failing silently, and the attacker is getting free shares because the top level transaction is getting executed, right? So this is one way we can do some gas griefing, all right? There are other stuff as well. So this is again a CTF challenge you might want to try out. The name is Maya, and it's again available on CipherShastra. Great. Moving on to the second gas griefing, the second pattern that we have. So with this one, we can actually perform some DOS, right, denial of service. How we can do that? All right. So previously we discussed about subcalls. We can use subcalls, and we can give a considerable amount of gas so that only the top level transaction works and not the subcall. But let's use this subcalls to exhaust the gas deliberately and not allow the top level transaction to execute ever, right? So yeah, what could be a possible scenario for this? Let's imagine, yeah, our very famous, our beloved challenge king of the ether, right? So you know how we solve these challenges. Like there is a king, a defined king, and if you want to dethrone that king, you're supposed to send more ether to whatever the last king has sent so that he will be dethroned and you will be the new king. Now, in order for the last king to be dethroned, it is necessary and important that that transaction, the transaction where the ethers of the last king will be sent to him, should be executed, or is necessary to be executed, so that in order to move to the next operations. But just imagine if we are not allowing the previous transaction to execute such that the whole transaction will not work. Now you must say we can do that by reverting the last transaction, right? But that's the point, right? We are not checking the status code. We're not checking whether the last call executed or not, right? So if you're trying to revert, the last king is trying to revert, that's not going to happen, right? Because even though you're reverting, I'm not checking the status code of the transaction, and it will always execute, right? It will always work. So, but still we can do something, right? How we can do that? Utilizing the return data copy. So what it does, as the name says, it returns the data from the last call that just got executed, right? So here you can see, but the problem is whether you need it, whether you want it or not, return data copy will always be there after a call is executed, right? So let's say there are two instances. First one, we don't want, we are not requiring the call data. Second one, we want it. We want this parameter return data. But it doesn't matter. In both of the instances, there will be an instruction return data copy, right? So it's like whether you need it or not, it will always be copied, right? So now how we can do that? Let's take the same example, right? Let's take the same function. There are some operations going on. Then there is a subcall. And then there are a few more operations. And as we discussed, the middle operation, the middle subcontext is needed to be executed such that the whole top-level transaction should work. But what we are doing in this subcall, this one here, the attacker is trying to randomly copy a huge chunk of memory, right? Now you must be wondering, okay, yeah, I got the point, but the subcall can only consume 63 of 64 of gas. So let it consume, let it consume everything, but there will still be 1 by 64 left for the top level transaction to execute the rest of the stuff, right? But it doesn't work like that because the copying of memory doesn't happen here in this gas. It actually happens in the top level transaction, right? So whatever the attacker is trying to copy, it is actually not utilizing the gas it's getting from the 63 by 64 gas. It is actually utilizing the gas of the top level transaction, right? So what we can do, we will randomly copy a huge chunk of memory in order to not allow the top level transaction to have anything left to process the rest of the opcodes. And what will happen? It will revert, right? So even though I've created, the name is Kingslayer, yeah, a modified version of King of the Ether challenge. So if you want to try, you can try it out. Cool. Now let's talk about a new thing that recently got popped up. And I'm pretty sure that will be a new attack vector, just like read-only reentrancy. You can think this one as a different pattern of read-only reentrancy. It works kind of like the same way, right? So now what it is all about, right? So I wondered that a same transaction gives you a different value if you call it twice, right? Now you will say, yeah, it's fine. Like if you're calling a function, what I will do, I will just check whether my function has been called once. If yes, I will give you one value. If you are calling it twice, I will give you another value. Simple as that. Yeah, I'll just keep a state counter, right? And I will just check it, like if you're calling it once or twice. But what if it's a view function, right? What if it's a view function and you cannot do or update the state or do nothing, right? Can you still manage it to give the victim two different values if called twice? Yes, we can still do it, right? So this is how we can do it, right? So what we are doing is, let's imagine, like this is a very random example that I've created. There might be some real-world examples, but yeah, just for the understanding, here you can see there is a function exec, and what it's trying to do is firstly fetching the oracle price, and just to make sure you're not giving, or the oracle is not giving a random value, we are just having a check that the value should be at least equal to or more than the minimum price, right? And then again, we are just updating a variable current price with, again, fetching the oracle or price. Simple as that. But what the oracle is trying to do, firstly, is checking what's the gas left right now. If it's less than, like we know for the first time, this call, oracle.price, for the first time, when the function will be called, there will be enough gas, like more than at least 11,800. So what it will return 500. To verify and validate the check, the conditional check that we have, that it should be at least 500. So we are verifying that. But the next time, you're calling the function again. But what I will do, now, as some of the opcodes, some of the instruction has already been executed, so there is less gas left than the 11,800. Now the view function will give you 0. So even though you have verified the check, the conditional check, you are still having a manipulated value that I have sent you, right? So here, the oracle can give you 0. So what's the problem? The problem is the uncached values. So this is a new attack vector that people should take care of while auditing code, while doing code reviews, right? So what could be a solution, right? Doesn't matter. If there is a function call, right, just cache it down and use it for the rest of the operations, right? Do not like fetch again and again, because now we know it. This can be done. Right, and moving on to what are metamorphic contracts, right? So this is again a cool new thing, right? So we all know about the upgradable contract, the proxy pattern, the typical ones. There is a proxy, there is an implementation, the delegate calls, like when you call a function of the implementation, the delegate call will work and perform the logic in the implementation and take the state of proxy, a simple pattern, right? So if you want to update the logic, the implementation, what you usually do, you go ahead, upgrade the contract, implementation contract, and what happens, there will be a new address, right? So if someone wants to check, it will be a bit skeptical because there will be a new address containing, so like, doesn't matter, there will be a new address. So people will get to know that something has happened in the past, right? But what if we do it on the same address itself, right? We change the code altogether, right? So now you must be saying, okay, like how we can do that, right? That's not a fundamental property of blockchain. You're not allowed to overwrite the code. Yeah, kind of, but we are using self-destruct, so we are making use of it, right? So, okay. Yeah, a good explanation is given here, implementation, sample implementation, so we'll have a look. All right, here it is, and cool. So how it works, firstly, there's a bytecode, a metamorphic bytecode, like what it is trying to do, we'll have a look in a moment. Then the first operation, the first thing it's trying to do is get your contract which you are trying to modify or morph after some time, which you want to upgrade. So firstly, it will deploy that contract, the implementation contract, store the address into a mapping here. Why we are doing it, we'll have a look. Then it will deploy the metamorphic code, right? So let's talk about what's the bytecode that we have just seen, what it's trying to do. It's pretty simple, right? Firstly, let's run it. Yes. So here you can see it's putting some parameters on the stack, and that's a problem. So we have to scroll up and down. But yeah, let me do it. Yes, right. So it stored 4-byte signature in memory, and rest of the parameters are the parameters of the static call, right? The gas address, the parameters of static call that we have. And what are these 4 bytes? What the signature is all about? Well, this is the signature of this function, get implementation. Yes, this one. So there is a function get implementation, and now how it works, when you deploy your metamorphic code here, it actually calls the constructor, right? Because whatever we have will be called as a part of constructor. So this one will be executed, right? So we are storing the function signature that we will be calling out later, right, in the static call. So what we are trying, we are fetching the implementation that we have recently deployed, which was the first step here, right? Remember, we deployed our implementation contract, this one. So what it's gonna do, it's gonna fetch the value from the mapping, making a static call, right? And then it simply fetch the size and simply do IXT code copy to copy the code of that implementation and overwrite itself, right? A simple process that happens, right? So what it's gonna do, it's gonna deploy a boilerplate metamorphic code, and the opcodes will run as a part of constructor, and these opcodes will take the value, the address from the factory contract, fetch the address, and take the code and overwrite itself. A simple process. Now, if you want to morph this code, if you want to override, if you want to upgrade the contract, you just need to go back to the factory, redeploy a metamorphic contract, and redeploy implementation, and you know what will happen? It will take the same exact address. Why? Because we are utilizing create2, and we can pre-calculate the address, right? So it's gonna use the same address. The important part is the first one needs to be self-destructed, because we cannot redeploy on the same address. So you have to self-destruct the first address, and then you can perform the same operation again. It will calculate the same address, deploy a metamorphic code, and that metamorphic code will take the address and override the new data. The problem is the state will be lost because we cannot deal with it. We are self-destructing, so state cannot be maintained, preserved, right? So imagine there are some non-technical people just randomly following a protocol, having trust in it, and let's take the same example of Oracle. The Oracle is giving you a price from A plus B, and the non-technical guys woke up next morning and finding now it's giving a price of A plus 2B. And what happened? They really don't know because it's the same address. Everything happened on the same address. It's the same state. Now, let's imagine there are some libraries. We don't even need the state. We are just referring to a contract to fetch some functions, like as I mentioned, A plus B or A plus 2B. So yeah, it can do some damage, right? It can, the developers, the team, can manipulate and modify the prices that you're getting. So always, for the auditors, if there is a self-destruct and if it can be controlled by the authorities, by the team, you should always flag it, right? Because nobody knows what could happen with this stuff. All right, so this was a metamorphic contract. This was, again, something that's very considerable and concerned. And we have actually seen this. I cannot disclose the project, but we have actually seen this stuff live in a protocol that we audited. And yes, we have flagged it because we don't know if the team is trustful or not. Yeah, we trusted, yeah, because they came up to us for the audit, but nobody knows. Right, so this was something we discussed. These are the steps that we just discussed. Cool. All right. Yeah, another cool thing, code injections, right? So we always talk about Web3 when we talk about Web3 attack vectors, right? Web3 kind of feels alone in this world, right? Because we are kind of missing our old school attack vectors, our SQL injections, RCs. Why not in Web3? Like, let's use them together and let's have a beauty from both the worlds, right? So what we can do, let's imagine some accesses, right? So let's imagine there is a platform like OpenSea, right? And there is an NFT with the token URI that you can control, and you can add any data that you want. And on the front end, on the application, there is no input standardization or input validation, so free to pass in any data that you want. And what you're trying to do, you're randomly passing a script in the storage, and that is being fetched on the front end without any validation. So imagine creating a login form, right, in the platform and saying, hey, go into this site. This is an NFT that I created. You just need to log in with your credentials, and you will get your NFT. And that credential or that login form has been created just utilizing the vulnerability of the application and not from the Web3 world, right? So this is one example. Cool. This is a practical, you can say, understanding that you can think about. This is how OpenSea fetches the data from URI. So, and it creates a page here, right? So you can see there is name, author, there are properties, there are traits, everything is there from the metadata, right? And that's what we discussed. If I create, or if I pass in some values which are not being validated, I can create anything possible, and the page will render it. So what could be a solution? Use some inner text and don't use inner HTML. Do not render what you're getting. Do not execute like inner HTML. Like even inner HTML is fine if you're keeping some validation. Now imagine you're directly proposing or directly doing some exec, JavaScript execute. So whatever script is there in the storage, you're directly running it. Now, what could have been done? There could have been an RC, right? So you could have created a shell on the application and can access the system. So that can also happen as well. And we have seen this kind of stuff in some protocols because they don't care about the front end, because they think that my protocol is like, doesn't make sense for them because it's just a plain front end and they're just fetching data from the storage, like some usernames, right? The protocol is allowing you to create any username you want, right? So instead of doing a username, you're just creating a script supposed to be executed on the front end, right? So that is one. And there could be anything that you can do if there's no sanitization. Cool, and let's talk in the end some bad patterns that we should take care about. There are multiple, but I've kept one. Static calls. So static calls are a nice little thing. They do no harm. They are cute. Yeah. So, but let's imagine we are writing some assembly code. We love writing optimized code. We are not like writing in high level, right? So what the feature of static call, it doesn't allow you to modify the state. You just have to work with the static state that you have. You are not allowed to update it. Cool. So, but what if we are using a stale memory in order to execute the rest of the operations? Or my other functions are depending upon the stale memory that we just have discussed, right? So what could happen? So I've created one example here. I'm storing a value at location 0, and this x is just to demonstrate like what was the value previously, making a static call, and then again fetching the value at 0 to verify what's the new value, right? So this is what happened in general in a normal scenario. There's a function random which is returning a value UN 5000. These are the outputs. Like firstly, the value was FFFF in the memory location 0. We called the static. We did a static call, return 5000. This was a new value, and Z is the status, whether the call succeeded or not, right? So this is all normal, right? But what if the function is reverting and doing nothing, right? So you're doing a static call, you're doing all the same thing, but these are the results. So earlier it had FFFF, the call failed. You can see the status is 0, the Z value. So the memory is still having FFFF, right? So now imagine you're believing your function that it will always give you some value, right? And you're proceeding with the value return with it, right? So imagine, again, the same example of price. You're saying, hey, the oracle will at least give me some value at some point of time, right? And I will not work with the random value that I already had previously. Now, in which scenarios it can happen? I used 0 location. 0 is usually kept for hashing, the first 64 bytes. So imagine there was some hash, there was some stale memory, there was some random data already there in the memory, and you believed the static call will give me some value, the return value, and I will proceed with it, right? I will take that input, and the rest of my operations will work with that value. But imagine the function is reverting, so you are actually working the value that you had previously and not the value that you recently got, right? So this is how, this is a bad pattern that you should always take care about if you're making a static call. And what you can do, simply check that what's the status code. If is 0, should not move ahead, and keep it right there. So I guess with this, these are my attack vectors that I think would be worth sharing about. And if you have any question, feel free to raise your hand or just shoot it out. All right, thank you so much. And with that, thank you for listening to my talk and being here. We'll see you around, and yeah, later.